In the previous lecture, we have seen how the akka cluster works, and what was evident there is that everything takes time. It takes time for a node joining to disseminate the information among the rest of the cluster, and then it takes time until the welcome message arrives and so on. And the decisions are taken in some consistent fashion, but they are not taken immediately. The cluster is one example of a system which is eventually consistent, and in this lecture we will look at what that means. When we made our bank account thread safe by introducing synchronization, we made it strongly consistent. That means that after an update to the field, all subsequent reads will see the updated value. You can see here a minimal example of such a system. We have a private field, accesses to which are protected by synchronization, and the update method accepts a function which transforms from the current field value to the new one. And in the synchronized region, we read the field, apply the function, write the new value back, and then return the written value. Any access reading this field will also synchronize on the same object. That means that all reads and all updates are serialized. They are executed in one specific order. And every read observes the value which was put in by the most previous update. This is called strong consistency, and it can be easily achieved here because we are doing it in a fully local system. The locks offered by Scala's objects only work because we are executing all code here in the same Java virtual machine on the same computer. But even so, we have already discussed that this can be problematic because synchronization blocks the thread which wants to execute it, potentially, and that is not good for CPU utilization. We can remove the need to block the calling thread by moving the synchronization into another execution context. Here, this synchronized block is executed in a future. That means that the update method, which takes this function, does not return the new value itself. It returns a future of that new value. And the thread can continue normally without having to wait for the update to occur. In order to properly publish the new value of the field, we write it here back, and if we mark the variable as volatile, that makes sure that other threads see the updated value when they do their next read. Therefore, no synchronization is necessary for the read method here. By removing the blocking nature of the update method, we have also removed strong consistency, because calling update and then immediately calling read will probably not give us back the new value. It will take some time until the new value is visible. This is called weak consistency, and that means that after an update, certain conditions need to be met until the new value is visible, and this is called the inconsistency window. Eventual consistency is a special kind of weak consistency. First of all, it takes a while until all reads return a consistent value. And second, this only really works once the system becomes quiescent, so once the updates stop. And then, after a while, once everyone has communicated the new value, then everyone is on the same page, and consistency will be achieved. Let us try this out with a simple actor. This actor also, the main purpose is to hold this field, an integer, but the goal is to have different actors collaborate and share the value of this field, such that updates can be performed on any of these, and eventually the update will be seen on all other copies. For the outside protocol, we need an update command, which gives a new value. Then we need a GET request and a result reply type. The actors which are part of this distributed store network, will communicate additionally using synchronization messages, and they will learn of their existence using hello. Now, how can we serialize the updates to this field? Because there are multiple copies of this field, one in every actor, and once two writes happen on different actors, these two actors need to agree upon which value to keep. Say we have an actor D1 here for distributed store 1 and D2. And this one gets a command update 42, and this one gets another update 43. They will both locally process these messages, and afterwards they will talk and sync up, and they need to keep either the 42 or the 43. In order to serialize these updates, we use here the current time in milliseconds. Whenever an update is made, we capture a timestamp and associate it with this value of the field. And then when D1 tells D2, I have a new value for you, then D2 can check, is this actually a new value or do I have something better? This is a simplified implementation of this protocol. Every time an update comes in, we write to the field and we take a current timestamp. When a GET request comes in, we reply with the current field value. So far, so simple. Now, when a synchronization message comes in with a potentially new value, we check that this timestamp is newer than what we know. And if that is the case, we apply it and keep track of the new timestamp. In order to set up the system, a hello message must be sent from D1 to D2, for example, and then D2 knows, this is a new one which I need to keep updated. So in reply to the hello, we send the first sync, and whenever we get a new update, original one, we tell everyone who wanted to know about it. We can try this out in the Scala REPL. First, we import all important akka things. Then, of course, we need an actor system to run things in. And I made this implicit to use something called the actor DSL. This is a small toolbox if you want to create actors on the fly in the REPL. It can be done like this. What this does is it creates a new actor. I didn't give it a name, hence it got the name $A. And the function of this actor is to just print out any message that it gets. This is made available as an implicit actor ref, so that it will be picked up when we send a message here from the prompt. I have loaded the code in a package, which I'm importing real quick. And now let us instantiate two such actors, called A and B. If we send a GET request to A, it will reply with a result of 0 to this anonymous actor we had up here, which will print it out. The same result for B right now. If we now update A, we see that it was updated, but B does not know anything about it. Now we can introduce these two actors. So effectively B sent a hello to A. A should have replied with the value, and we see that has worked. Now if we update B, that is reflected here, but now A was not updated because the introduction needs to be done both ways. Now the update has propagated back to A. And now we could update on any of the two, and the other one will eventually learn of it. After playing with actors in the REPL, we need to shut down the system. Otherwise, the REPL will not properly terminate. Actors and eventual consistency are deeply related concepts. We have seen that within an actor, we have, so to speak, an island of consistency in an ocean of non-determinism, which is the messaging outside. So everything you do within an actor is sequentially consistent. Everything happens like it was on a single thread. But as soon as you have actors which collaborate, they can never be strongly consistent. They can never agree on a shared thing because they always need to exchange messages. And a message takes time to travel. So by the time it arrives, the state which should be agreed upon might already have changed. Therefore, collaborating actors can at most be eventually consistent. But that is not automatically the case. You need to work to make the behavior eventually consistent. Looking back at the distributed store, which we have just seen, that had a few flaws. For example, if updates come within the same millisecond, then the merge was not properly resolved. Another problem is that message delivery is not guaranteed, but there was no resend mechanism. And this would also be problematic because eventual consistency requires that eventually all updates are disseminated to all interested parties. And this usually implies that there needs to be a resend mechanism. Another way to do it has been shown in the cluster, which does not resend because of failures. It just resends pessimistically, so to speak. The gossip messages are always sent, no matter whether we know that the other party, for example, needs the update or it might all be old news. And the last observation is that in order to achieve eventual consistency, the data structures which are shared need to be suitable for that. There is a class of such data structures which are called commutative or convergent replicated data types, described in this paper. If you have watched the second part of the Actors Are Distributed lecture, then you have seen another example of this one, which is the cluster membership state. In the following, I explain how that data type works, but this is optional, as was the part of the distributed lecture. As a reminder, we had 6 states. It began with joining, and then we had up, leaving, exiting, removed, and we had down. The property which makes this data type manageable as a convergent data type is that all transitions form a directed and acyclic graph. So the normal way a node takes through this is from joining via up, leaving, exiting to removed. But there are other ways. For example, from these states, you can always become down and then removed. When cluster nodes exchange gossip messages, these messages contain the state of all nodes currently known to the cluster. So for each of the members, there will be one of these values. For example, we have a cluster here with a few nodes. And this one learns something about, say, node 4. And this one learns something else about node 4. Then the information might spread. And let's say node 2 learned the green thing first, and then the red thing. These are 2 new informations about node 4, which need to be merged. Let us say that the red information was that it was down, and the green one was that it was leaving. because this is such a nice graph, we can give an order to all the possible pairs of states, saying that down takes precedence over leaving because you can go from leaving to down, but not the other way. This gives us the property that a conflict, for example, as here, can be resolved locally first. And the second one is that conflict resolution is commutative. So it does not matter whether you learn this first or that. The merge result will always be down in this case. And this is the property which makes the cluster communication eventually converge, even if conflicting information was injected at several different points in the cluster.